Hello guys, welcome back to Maison African Motives. Still working on industrial electronics and one. In this case, we've got the question paper, which was written actually in July 2021. So we just want to work out these typical questions so that we can prepare ourselves for the exams which are ahead of time. So let us quickly rush through the questions and see what you're given. So as we know, guys, you must be able to read your instructions and so forth. So here we are given our instructions and information, which is important, especially to number the answers correctly according to the numbering system used in this question paper. All right. So the first part that you're given is question number 1. Sorry for that. We are given various options are given as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question number, okay? The nucleus of an atom, okay? So we are given here, what is the nucleus of an atom? It consists of electrons and neutrons. This is actually wrong. Consists of protons, electrons, and there's positive charge. That is actually wrong. Is no charge. That's wrong. Is made up of neutrons and protons. So this is what we actually have in this case. It's supposed to be neutrons and protons. So here we are having our answer as a D. So actually, this is what you do. You are working with each question properly so that you see which one is the best answer there. Ohm's law relates to the relationship that exists between voltage and current and the resistance, and states that, okay, what does Ohm's law state? Okay, so Ohm's law is all about voltage being proportional to current and inversely proportional to resistance. And this is what we have in this case, that voltage is directly proportional to the current and inversely proportional to the resistance. All right, so that is what we have in this case. All right. Resistance inversely to, okay, current directly proportional to voltage and inversely proportional to temperature. Current directly proportional to resistance, inversely proportional to the voltage. All right, so it's proportional to the resistance. So of all the answers that we have, we can see that the D is the one that we can have as our final answer. 1.13 extrinsic semiconductor materials are, so if we are dealing with extrinsic semiconductor materials, we are talking about a combination with impurities here. So which means the C part can be the best one. Combined with impurities. Yes, that's a combination of impurities. Polarization occurs when does polarization occur? All right, oxygen bubbles from around, okay, the electrolyte. Hydrogen bubbles form around a positive electrode. So this is what we have here. We've got our polarization here. All right. 1.15, an increase in voltage at terminals of an electrolytic capacitor will, if you increase voltage, what happens? There will be an increase, the charge, but the capacitance will remain the same. All right, so this is the exact part that we have here. Increase the charge, but the capacitance is going to be the same. All right. So that is what we have on question number 1. So as you can see, guys, question number 1 is just a matter of working with your theory part and so forth. Complete the following sentences by writing only the missing words or the missing word or words next to the question number. An electrolytic capacitor consists of plates that are separated by air, okay? So it consists of 2 plates in this case that are separated by a dielectric in this case. So this is separated by a dielectric, all right? So it's just a normal capacitor, all right? NPN transistor are constructed from semiconductor materials and can be used as, so remember, transistors can be used as switches or we can use even as amplifiers. So here we can have switches, we can also have amplifiers. These are the uses of what? Of transistors. An atom with an atomic number 14 has how many valence electrons if we are given the atomic number of 14? So if you are to draw at the end, remember that the first part is going to be 2n to the exponent of 2, whereby we are going to consist of 2 electrons. So we are going to take 2 electrons in the first one. The second one, it is going to be 2 times 2 to the exponent of 2, which is 4 times 2, that is 8. So which means we have covered 10 so far. So out of 14, we are going to remain with the 14 minus 10, which is 4. So in this case, we are going to remain with 4 valence electrons, all right? Secondary cells can be, but cells cannot, all right? So definitely, it can be rechargeable, but primary cells cannot. So secondary cells, you can recharge them. So this can be recharged, all right? So this can be recharged, but the primary cells cannot, all right? You can't do that. All right, temperature and 4 factors that affect resistance of a conductor, all right? So this one, we can take it from the resistance of a conductor, which is rho L over the area. So we are talking about the type of material. In this case, we are talking about the length, we are talking about the area. So in this case, we are given temperature. So which means our answer here can be the type of material from this one. This is type of material, that is our rho. It represents the type of material. Type of material. In this case, we can talk of the length of that conductor. So we are talking about the length of the conductor. We are talking about the area. So we are also talking about the area, which is the cross-sectional area. So these are the 3 possible answers that you're supposed to have on this question. All right, 1.3. A copper conductor has a resistance of 48,6 at a temperature of 50. Determine the resistance of the conductor at 0 degrees. If the temperature coefficient is, okay, we are given the temperature coefficient in this case. Okay, so remember that, all right, we are given from our information. Let's just take our information in this case. This is 1.3. So we know that the resistance at a certain temperature is equivalent to the resistance at 0 degrees Celsius into 1 plus the temperature coefficient times the change in temperature in this case. So if you are to check here, we are given that a copper conductor has a resistance of 48,6 ohms at 50 degrees Celsius. So this is the resistance which is corresponding at a temperature of 50, which is at this temperature here. So we are given that this resistance is 48,6. So this is going to be 48,6. We need to calculate the resistance at 0, so we do not have this. 1 plus the temperature coefficient of this copper is given as the temperature coefficient of copper is 0,00428, 0,00428. So this is what we have, 0,00428 times the temperature. This one is the one that is corresponding with the resistance of 48,6, which was at 50 degrees Celsius. So this is what you're going to have in this case. So we are supposed to calculate the resistance at 0 in this case. So you can divide by the whole of this bracket, that is 1 plus 0,00428 times 50 in this case, both sides. We can actually have the value for the resistance at what? At 0 degrees. All right, so this can cancel here. So that means we are remaining with the resistance at 0, which is 48,6 divided by this whole bracket. And this is going to give us 40 ohms in this case. All right, so that is how we can calculate this typical question. On 1.4, we are given to indicate whether the following statements are true or false by writing only true or false next to the question number 1.1 and up to, okay? In a closed circuit, the electrical pressure measured across a cell is called electromotive force. So the electrical pressure, okay, so we are talking about the electrical pressure that we are going to have that is measured across a cell, electromotive force, okay? This is actually true, EMF. The conventional theory of current flow states that the electron flow from negative to positive in a closed. No, electrons are supposed to be from positive to negative in this case. So that is the flow from positive to negative. So this is actually false. All right. Ohm's law is a relationship between voltage, current, and the resistance. That's true. We saw this question before. It was a relationship that was between current, voltage, and also the resistance. A voltmeter is always connected in series in a closed circuit. This is actually false. In order for you to measure voltage, you measure it in parallel. You connect a voltmeter in parallel across the resistor. So this is false. An ammeter is the one that is connected in series, okay? A galvanometer can measure large currents. Oh, no. A molecule is the smallest particle of an atom, which is actually a molecule or not of an atom. Okay, this is actually wrong in this case. It can't be. All right. So that is what we are given in this case. And we move on to the other part. Okay, where is this part? It's here. All right. On question 2, we are given that there are two resistors that we have, which of 6 ohms and 12 ohms in this case. All right, so these two resistors are connected in parallel to each other. This combination is then connected in series with a 16 ohm that has a tolerance of 2% complete. The complete circuit is then connected to a 50-volt DC supply. All right, so draw the circuit to represent the above information. All right, so you're given two resistors that are in parallel and another one in series. So a circuit, it depends with how you want it to look like, guys. It's not like you are having just one setup of a circuit. All right, so let's say I'm having my voltage source here. So like I said, it depends with your presentation. How do you want it to look like? So I want to have my voltage source here. I am given a resistor that is in parallel, then two resistors which are connected, in series, and two resistors which are connected in parallel in this case. So there are two resistors which are connected in parallel like this. This is what we are given from our information. We are given that two resistors with the value 6 and 12 respectively are connected in parallel. So these are the two resistors, the 6 and the 12. So we've got 6 ohms here. We've got the 12 ohms, depending with how you want it to be like. And we are given the series one that is having a resistance of 16 ohms, and we are also given a tolerance of 2% in this case. All right. So this whole setup is then connected to a 50-volt DC, which is in this case, we are given 50 volts here as our total voltage for the given circuit. All right, so that is what you are given. 2.12, calculate the total resistance of the circuit. All right, so the total resistance, if we are to check in this case, we are going to see that this is a parallel plus a series. So the total, that is 2.12 in this case. So the total resistance is going to be, let's say this is R1, this is R2, this is R3. So our total resistance is going to be R1 plus RP. The total of these two resistors which are in parallel, we are going to calculate the total for these two resistors, which means we've got RP, which we know that RP is a product over the sum. So it's a product of R2 times R3 over R2 plus R3. So depending with how you numbered your resistors. So here, that is what you're going to have in this case. So that means RT is going to be R1 in this case, which is 16 ohms. So I'm having 16 plus RP, which is the parallel combination, which is the product over sum. So it's 6 times 12 over 6 plus 12 in this case. All right, so let's see what we are going to have at the end. So from the parallel combination, we are going to simplify this from our calculator, 6 times 12 over 6 plus 12, which is going to give us 4 ohms. So if we combine everything, that is going to be 20 ohms. So this is the total resistance, noting that this 4 ohms is representing our RP in this case. All right, so that was question 2.12, whereby you are being asked to calculate the total resistance of the circuit. All right, then 2.13, we are now given to determine the current flow in the circuit, and that is 3 marks for that, the current flow. All right, so how can we calculate the current in this case? That is the total current. We have got the total voltage, we have got the total resistance, so we can take advantage of that. All right, so remember that from voltage and resistance, that current, remember that we talked about from our Ohm's law previously. So this is question 2.13. So our current is going to be the total voltage over the total resistance. All right, which is the total current is going to be the total voltage. We are given that here is 50 volts. That is our total voltage. So we are given a total voltage of 50 over the total resistance, which we calculated, that is 20 in this case. So that means our current is going to be 2.5 amps if we divide this properly. All right, so that was what we are given in this case. Then what is the color code of the 16 ohm resistor? All right, what is the color code on 2.14? That is 4 marks. All right, the 16 ohm resistor is this one that we mentioned before, where we are given that it's 16 ohms and we are given that it has a tolerance of 2%. All right, so we are given its tolerance in this case. So, okay, so this is 2.14. So it's a resistor of 16 ohms and with a tolerance of 2% in this case. So remember that the first digit that we have is a 1 in this case, and 1 corresponds to the first digit. I mean, we have got black, brown, so this is going to be a brown in this case. Then 6, which is at blue, remember digit, digit, so this is a blue, which is our digit. Then we are supposed to have the multiplier in this case. So in this case, we are having 16 times 10 to the power of a 0, which gives us a 1. So that 16 times a 1 gives us a 16. So this is 10 to the power of a 0 in this case. And 0 is on black. So this is going to be black for the multiplier. Then the 2% now for the tolerance, it corresponds with a red. So that is these are the colors that you're going to have from your color coding. So this you're supposed to be well used to your color coding. If I'm going to have a soft copy next time, I'm going to show you the layout of your color coding so that we actually take those values as you see them from the exact values of a color coding concept. So I just hope as we are revising next time, we are going to have that on a soft copy so that you can properly see what I'm representing. All right, on question 2.2, we are now given that there is a circular copper conductor with a diameter of 6 millimeters that has got a length of 25 meters. The resistivity of the conductor is 1.728 times 10 to the power minus 6 ohm meters. Determine the cross-sectional area of the conductor. All right, so here we can take our information. We have got the diameter in this case, which is 6 millimeters, the length of 25. All right, so we are given, this is question 2.2. So it's actually copper, which is a circular conductor that we have. So we are given the diameter of 6 millimeters, which is same as 6 times 10 to the power of minus 3 in meters. Remember to remove milli, that's times 10 to the power of minus 3. All right, we are given the length of this conductor, which is 25 meters. In this case, we are given 25 meters. And from the whole information, we are also given the resistivity of the conductor, which is the copper, which is 1.2. So we are given, in this case, the resistivity. All right, so the resistivity that we are given in this case, it's 1,728 times 10 to the exponent of -6 ohm meter. All right, so the first question that we are given on 2.21 now is to find the cross-sectional area of the conductor, which is a circular conductor. So if it is a circle, we are simply referring to the area of a circle in this case, where from the diameter, we can say that our area is equivalent to pi d squared over 4. So that is going to be pi times the diameter in the meters, which is 6 times 10 to the exponent of -3 squared everything over 4. So we are going to have the cross-sectional area of a circular shape that we are given. So that's our area, which is going to be, if we simplify properly, this is going to be 2,827 and so on times 10 to the exponent of -5. So this is in square meter. So this is what you have from your calculator, of which you can leave your answer like that, or you can write it as 10 to the exponent of -6. It depends with how you want to represent your answer in this case. So if you are to check, if you are to use the value of pi in this case as 3, depending with the information that we are given, let's just check here, but I thought like here we are not given. Let's check. Here we are not given here to say your pi is going to be 3,14 and so forth. So you can just use your pi as it is from your calculator. All right. But if you are to use the value of pi to be 3.142, then your answer is going to be something like 2,82. 2,828 on this one times 10 to the power -5. So like I said, it depends with the values that you are using. All right, so that was the cross-sectional area. Then we move on to the resistance of the conductor, and that is 2.22 having 4 marks. So how can we calculate the resistance from this information? We have the area, we have the length, we have got the resistivity of the conductor. So remember that resistance is equivalent to, all right, so this is question 2.22. That resistance is equivalent to the resistivity times length over area. Remember from those conditions that we talked about to determine the resistance. So we can substitute our values, that is the resistivity of our conductor. In this case, that's 1,728 times 10 to the exponent of -6. So that is what you're going to have, 1,728 times 10 to the exponent of -6 times the length of the conductor, which is 25 meters. We are given our length of 25 meters in this case, over the area, which is the one that we calculated here, that is 2,827 times 10 to the exponent of -5. All right, so this is what you're going to do. Substitute your values, then you can calculate your area, and this is going to give us, if you simplify properly from our calculator, that's 1,528 ohms in this case. So remember, this is resistance, and resistance is measured in ohms. So take note of the units, guys. If you are dealing with resistance, resistance is measured in ohms. All right, so that was our question 2. In this case, having a total of 25 marks, everything here is on question 2, 25 marks. On question 3, we are given that 3 capacitors with capacitance with the following values are connected in series to the, okay. So if we are dealing in capacitors, they oppose resistors, okay? If you are dealing with capacitors in series, you work them the same way you do to resistors that are in parallel. That is what you do. So they are in series, but you calculate as you are calculating resistors that are in parallel. All right, so the question is to calculate the total capacitance. Remember, for you to have the total resistance in parallel, it's 1 over RT, which is equal to 1 over R1 plus 1 over R2, and so on. So it is the same thing for capacitors that are in series. So we have got 3 capacitors here. So that means we are going to have, this is 3.11. So 1 over CT, which is 1 over the total capacitance, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. All right, so that's 1 over CT. The total capacitance is 1 over C1. Thus, you are now referring to your capacitors. That's 5, 15, and 25. So it's 1 over 5, first one, plus 1 over 15, plus 1 over 25. So we're going to calculate the total in this case, which is going to give us 23 over 75 from your calculator. So this is 1 over CT, but as we need the value for CT, so you can even cross multiply to find the value of CT, or you can just introduce, so in order for you to have CT, you just divide by 1. So 1 divided by this, here you must have CT. So here we are just going to divide 1 divide by everything on this far part, which is going to give you the inverse, which is 75 over 23. And 75 over 23 is going to give us something like 3,261. But remember, these values, they were in microfarad, so this is going to be microfarad. Or you can simply cross multiply at this stage. We are given that 1 over CT is equal to 23 over 75. So you can just cross multiply in this case. 75 times 1, that's 75, is equal to CT times 23, which is 23 CT. So to find CT, which is the total capacitance, divide by 23 both sides, divide by 23 both sides. That means our CT is going to be 75 over 23, which is the same as this one. Then you can divide back to give you a decimal. So it's the same concept or the same way that you do if you are dealing with resistors which are in parallel, but this is for capacitors that are in series. All right, so that is how you calculate. Then the charge developed across all the capacitors in the circuit. So take note, we have got a voltage here, and we know that charge, which is Q, is equal to CV. So Q is equivalent to CV. So we can calculate the total charge, which is measured in coulombs in this case. So 3.12 Q is equal to the total capacitance times the total voltage. So that's Q, the total capacitance, which is 3,261 times 10 to the exponent of -6 times the total voltage, which was 50 volts. So this is going to give us the total charge in this case. So you're going to simplify, you're going to have something like 1,6305 and so on, times 10 to the exponent of -4, which is measured in coulombs. So charge is measured in coulombs. So you can even leave your answer like that, or you can maybe put to millicoulombs, depending with how you want your answer to look like. All right, so that was question 3.12. 3.2, we are now given that here a main transformer has turns ratio, which is, we are given that the turns ratio when the primary is connected to the main voltage of 200 volt. Okay, so the turns ratio is 5:1. All right, so remember that turns ratio is taken from N1 over N2. So we're given that N1 S2, N2 is given as 5:1. So this is how we are given this as 5:1. So it simply means that N1 over N2 in this case, all right? Okay, let me use this one. Let me use this one. So it simply means that N1 over N2 is equivalent. But here it's N1 S to N2. N1 S to N2, so it's going to be 5/1, just like N1 over N2. So it is going to be 5/1. That is what it means. All right, when the primary winding is connected to the main supply voltage, so we are given V1, which is, okay, let me actually use, guys, what we are used to. Let me take this as P. I'm now taking this from our other subjects there. So this is primary, secondary. So VP, which is for the main supply, which is our primary, that is 240 volts. And the current flows through the secondary winding. So we are given the current in the secondary winding of 1,5 amps in this case. So you can even use the V1, the V2, as long as you understand that V1 is primary, V2 is secondary, okay? Or you can use P and S, okay? Still one and the same thing. So the question now on 3.21 is to calculate the voltage across the secondary winding in this case, which means we have to calculate VS. We have the voltage in the primary. What about the voltage in the secondary? So we can take advantage of the turns ratio that we are given of 5:1, since we know that NP over NS is supposed to be equivalent to VP over VS, which is equivalent to IS over IP. So in this case, as we are just focusing with the secondary voltage, so which means we are focusing with these two here. So this is what you're going to take, or what you're going to equate. So from our NP over NS, which is equal to VP over VS, we are given the NP over NS. This is the ratio that we are given, 5/1. So you can take that as an advantage to say 5/1 is equivalent to VP, whereby we have VP in this case that is 240, everything over VS. And our VS is the one that we are supposed to calculate. So from your cross multiplication, we can find the value of VS in this case. If we cross multiply, that is going to be 5 times VS, which is 5 VS, 1 times 240, that is 240. So to find VS, we can divide by 5 both sides in this case. All right, so that is our VS. 5 into 240, that is going to be 48 volts in this case. All right, so we've got the voltage on the secondary side of the transformer. Then the current flowing through the primary. Okay, as we can see here, we've got the primary in the secondary. What about the primary in the primary side? We do not know this. So we can even take again from our turns ratio, because we can still have a condition of current here to say that when we are referring to current now, NP over NS is going to be IS over IP. So NP over NS, that's our turns ratio of 5:1. So that is 5/1 is equal to IS over IP. We have the current in the secondary of 1,5, but we do not have the current in the primary. So we're going to calculate this. So cross multiply again, 5 IP is going to be 1 times 1,5, which is 1,5. So if we divide by 5 both sides, to find IP, this is going to give us 0.3 amps. All right, so that is what you're going to have this case as the current that is in the primary side. All right, so that is our current in the primary side. So that was our question 3.22. All right, so let's check the other part of the question. That is question 3.23, the number of turns on the primary winding if the secondary winding is 100 turns. So still we are back to that same formula, guys, our turns ratio. Okay, so this is 3.23. So we are still back from that formula that we had to say our turns ratio NP over NS is 5/1. This time we are now given the turns now on the other side of the winding, which is the secondary, which is 100. What about the number of turns in the primary if the secondary is 100? So we're just substituting here to say the turns in the secondary is 100. So NP over the turns in the secondary of 100 is equal to 5/1. So you can calculate the value of NP, cross multiply again. That is going to be 1 times NP, which is NP is equal to 100 times 5, which is 500 turns. So that means in the primary, we have got 500 turns in this case. All right, so that was question 3.23. On 3.24, we are now given one fault that a transformer can develop is bent windings. Explain briefly what this term means. Okay, if we are talking about the bent windings, what are we actually talking about in this case? All right, so I want you to check what we are given in this case about this. So this is an excessive current that results in too much heat dissipation. That is, the insulation breakdown can cause windings to become short out, and overheat. So any of the reasonable answer that you have in this case, that is the one that was actually needed. All right, so that was The exact thing, I don't know if it is clear. Let's check another one, another question in this case. On this part, we are now given on 3.3 to sketch the EC circuit symbols of the following: an electrolytic capacitor, photodiode, and so forth, and so forth, and so forth. All right, so we are given to give this the sketches of these ones. All right, so I'm just going to just give you a basic sketch on each. All right, so if you're dealing with an electrolytic capacitor, in this case, what you're supposed to show is the issue of the positive negative concept. All right, so just a normal capacitor, guys. So that's it. All right, so we can just show our positive, negative. All right, a photodiode, just from a normal diode, but we are supposed to show the issue of the light now. The light, because it's supposed to be photo for light. So our normal diode is supposed to be like this. All right, but now our photodiode is going to be having the light rays into the diode like this. So that's a photodiode, okay? A variable resistor, it's just like a normal resistor, but this time what is happening is that we are going to have this to indicate a variable resistor, this arrow. So remember, as a resistor can also be shown in this case like this way. That can be a resistor, and you can just show it like this. Okay, a fuse. So a fuse, you can draw a normal rectangle like this, which is passing through out like that. That's a fuse. All right, an ion core transformer. So a transformer, it's all about the turns in the primary and also the turns in the secondary like this. So, and also having the ion core like this core part like that. All right, so that's an ion core. Then we have got light emitting. Take note, with this time, this is emitting. So to emit is to give out. So it's actually a normal diode, but it will be giving out light, this one. So this one is going to be like this. So it's going to give out light, emit light, okay, like this. So that's light emitting, all right? So I think everything is fine. On question 4, define the following terms. All right, so here we're given to define the following terms. The first term is polarization. What do you understand by the term polarization in this case? All right, so I have got our terms here. Polarization, that is the formation of hydrogen bubbles around the copper electrode, preventing a chemical reaction from taking place. All right, so that is what you're given in this case. All right, another part of the question, we are now given extrinsic, that is intrinsic, sorry, that's intrinsic semiconductor in this case. All right, so an intrinsic semiconductor is a semiconductor material, e.g. silicon, that has no impurities added. So it has no impurities. Once there are impurities, it is now an extrinsic semiconductor. All right, so that was what you're given in this case. And the other part of the question is 4.13, the potential difference. So what do we understand by the term potential difference? So the potential difference can be given as the difference of electrical potential between 2 points and is measured in volts. All right, so that is what you're given in this case. All right, on another part on 4.14, the covalent bond. What is it that we are referring to the covalent bond? So it is a bond that is formed when electrons are shared between 2 atoms. So that is what you are given in this case. All right, the other part of the question is doping. What do we refer to when we are talking about a doping? So it's an actual addition of impurities that you're going to have. So this is the addition of impurities to pure silicon material. So if you have a pure silicon material, add impurities, that is what we are referring to as a doping process. And the other part, which is last one, it's ionization. So ionization, from our definition, what are we saying, guys? If we are referring to ionization, this is now the process by which an atom or molecule acquires a negative or positive charge by gaining or losing electrons. All right, so I think this part was pretty clear. It's just a matter of working on more questions and working on your theory again. That can actually help a lot. On question 4.2, we are now given 4 cells each with EMF of 2,1. We once had a question like this, if you still remember, but it was having 2 parallel and another one in series. But this one is a direct question that we are given. It has got each has got EMF of 2,1 and internal resistance of 0,5 are connected to one another in series. This battery is then connected across an external resistor of value 20 ohms. All right, so what we need is to calculate the total EMF of the battery in this case. So take note that we are given that there are 4 cells, each with EMF of 2,1 volts in series. So which means the total EMF you're supposed to add 2,1 4 times. So to add 2,1 4 times is simply to multiply 2,1 times 4. But you're supposed to add E1 plus E2 and so forth and so forth. So this is going to give us 8,4 volts. All right. Then 4,22, 4.22, the total resistance of the circuit. So take note here, we have got the total resistance of the circuit. All right. So if we are to check here, our total resistance is affected by 2 things here: the total internal resistance and the resistance which is in series, the external resistor. So meaning to say, for us to have this total resistance, that's 4.22, we are going to have the total resistance for the internal resistors plus the series connected resistor of the 20 ohm, which is the external resistor in this case. So these resistors, the internal resistors that we are given, they are connected in series, each having an internal resistance of 0,5. There are 4 of them connected in series. So it is going to be 0,5 times 4. So this is going to be 0,5 times 4 plus the series resistor that is later connected, which is the external resistor that you've got a value of 20 ohms. So we are going to add to this one because it is in series. So 0,5 times 4, that is going to give us 2 plus 20 in this case. So 2 plus 20, this is going to give us 22 ohms as our total resistance. All right, so that was what we are given in this case, or that was the simplification part that we have. On 4.23, the internal resistance of the battery. Okay, so this is, I don't know why they are actually asking this question, because we talked about this, the internal resistance. This is our RT. So we actually calculated this before. So our RT, remember, we are given that it has an internal resistance of 0,5 and there are 4 of them. So it's just 0,5 times 4, which gave us 2 ohms. So it's actually a repetition because we calculated this before. All right. On 4.3, we are now given draw a fully labeled diagram showing 2 bar magnets with their north poles facing each other. The direction of the flux line must be shown clearly in the inside as well as outside the magnets. All right. So this is what I want you to check in this case from the diagram that I'm having here. All right. Let me show you the part of the screen. So this is what we are having. So we are told that the north poles are supposed to be each side north. So as you know, north and north, there is going to repel in this case. Okay, this is north connected to north. So this north is going to be trying by all means to be connected to link with the south, because these two, they are repelling. Okay, so the magnetic lines of force of flux and the like poles repel, that is, they push away. But negative, north and south, these two, they attract each other. But north versus north, there is nothing, there is no attraction. They do repel. All right. So that is what you're given, guys, from this question paper. for industrial electronics from the question paper that was of August 2021. So let us continue to revise as much as we can as we are preparing ourselves for the exams, which are just a few days ahead of time. So that is it for now from African Motives till we meet again.